Solar is an important source of clean energy and likely to play a central role in a future energy system without coal. Yet, not only does solar not produce energy when it's dark or cloudy, solar is also affected by air pollution.
This video outlines an experimental study of the impact of urban air pollution on solar PV output. The topic is of vital importance for two reasons. First, there is a trend towards distributed solar in large, developing world cities, which also suffer from air pollution. Second, while there are many scientific reports and studies on this topic, what the general public needs is something more akin to an online tool for analyzing this impact.
This will not only help people in polluted urban areas better predict what solar panels will produce, but it can also help national and global energy systems modelers make better long-term estimates of how much solar will be needed to reach the Paris climate targets. It can also help financiers and insurance providers offer lower-cost services to those who adopt solar. Many places with the best sunlight also suffer from air pollution, but much of what is known about how air pollution affects solar output relies on broad inference or estimates of pollution from satellite observation. Over the last decade, solar PV has become a major world energy source. As of 2020, the world had over 700 gigawatts of solar installed, roughly the equivalent of half the electricity generation capacity of the United States or Europe. Given that this is likely to grow rapidly over the next 2 decades, led by countries like China and India, it's important to be able to forecast accurately how much electricity these panels will produce. In the 1990s and early 2000s, most solar PV was installed in Europe and the US, but in recent years, solar has shifted to the developing world, including especially China, but also to places like the Middle East, India, and Mexico. Many parts of these regions suffer from higher levels of air pollution. Perhaps because these areas have only recently installed solar in large amounts, it remains surprisingly difficult to find good, practical, publicly available tools to estimate how air pollution affects solar production. Many studies are based on broad timelines, looking at the overall impact of air pollution over the course of a full year or even longer. This 2019 paper by Sweerts and colleagues looked at long-term reductions in sunlight in China by examining ground-based monitoring data going back to 1960, when presumably China had little urban air pollution. This type of study can help understand the total effect of air pollution on PV output over a year, but it doesn't produce estimates for PV production over shorter time frames or specific sites, or use inputs available to the public, such as ambient PM2.5. Other studies have produced results more directly focused on the impact of ambient air pollution on short-term output, but many of these rely extensively on modeling. This paper, by Lee and colleagues, studied the worldwide impact of particulates on PV output using a variety of sophisticated quantitative models, but the inputs are not the type of data available to the public. Some researchers have used direct ground-based experiments with solar PV located in polluted regions. This paper, by Duke professor Mike Bergen, studied the effects of dust soiling and ambient air pollution on PV output in Delhi, India, and then used several models to estimate solar output reductions due to pollution around the world. However, the model inputs are again different from those available to the public, for example, the total mass of particulate matter. In recent years, there have been more experimental studies, including in Singapore, India, and China. Here's one example by Peters and colleagues, who examined the impact of India haze events on solar output. A key highlight of the Peters study is how it relates solar output changes to specific ranges of ambient PM2.5, albeit focused on a narrow period of a single haze episode. Meanwhile, there are some useful calculation tools online that can enable solar customers to estimate their rooftop solar potential. Some of these, such as Google's Sunroof, include a variety of useful, practical factors, but air quality is not included as a variable. In the developing world, uncertainty about solar energy production is a major barrier to financing. Unlike the coal, oil, and gas industries, the solar industry relies heavily on smaller-scale projects, including individual commercial rooftops and homes. Especially in poorer areas, these projects will never have the resources for sophisticated forecasting, modeling, or on-site measurement. Financial due diligence will have to rely on more basic tools to estimate the cost and output over time. That's where this experiment comes in. GIZ worked with experts at the Solar Energy Research Institute of Singapore, the China Academy of Sciences Institute of Atmospheric Physics in Beijing, and Envision Digital to devise an experiment to test the performance of solar panels over the course of a whole year, and that includes during a variety of weather, sunlight, and air quality conditions. We placed a solar PV test panel and supporting equipment next to a 300-meter tall weather and pollution measuring tower in Beijing, and we collected solar data for every minute of the day for 2 years, along with weather data from various sources. We also compared that with other sites where data were available to our research partner, Envision Digital. This hourglass-shaped image is actually a graph of the data produced by the experiment. Each row of pixels represents a single day, and each column a single minute. The hourglass shape comes from the long days of summer and the short days of winter. You can see the shadow of the pollution measurement tower, which passes in front of the sun each day at a slightly different time and angle. In Beijing, the sun never actually shines directly overhead, so the tower bends back on itself as the sun's elevation declines in the fall. Days with brighter sun and fewer clouds are brighter, and days with scattered clouds appear as rows of interrupted dots and dashes. Clouds can actually produce bursts of bright light just as the sun strikes their white edges. The really valuable data are the bands of similar cloud-free days when pollution was rising and falling. By matching solar output data with data on air quality for these periods, we can estimate the impact of air pollution on solar output, controlling for other factors. What we found is that there is indeed a strong relationship, a 14% reduction for the first 100 micrograms per cubic meter, and a smaller additional 12% reduction for concentrations up to 200, and then an additional 10% drop for the next 100 up to 300 micrograms per meter cubed. In Beijing, the annual average is around 30 to 40 micrograms per meter cubed, but concentrations can go pretty high for some periods, even reaching above 300. When we apply this to past PM2.5 hourly records in Beijing, we can see how having a formula can illustrate how changing levels of PM2.5 will affect PV output. The effect has now fallen from a 13% reduction in 2010 to just a 6% reduction in 2021. Having a formula provides much greater precision than just an annual estimate. Applying the PV output reduction formula to the hourly PM2.5 data shows a significant difference from applying it to annual output, given the annual average PM2.5 concentrations. That difference is as much as 2%, and that's enough to have a big impact on financing. These results will help clarify global energy models and hopefully reduce the cost of financing for both large and small solar arrays, especially those in urban areas in the developing world where air pollution is an issue and where clean energy is most needed.